The Bob Murphy Show, episode 298.
There's a tidal wave coming. What you gonna do?
Get ready for another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. It's your source for commentary and interviews, conducted by a Christian and economist. Now here's your host, Bob Murphy.
Hey everybody, welcome to The Bob Murphy Show. Today my guest is Steve Landsburg, and woo boy, we have a broccoli and spinach combo for you. Namely, we are going to go through the life and mathematical contributions of Alexander Grothendieck. And this is Steve's favorite mathematician, and we're just going to let Steve rip. So this is one, you know what? If you don't get through this one and you just skip it, I forgive you. It doesn't mean you're not a serious thinker, although it doesn't help. Joking aside, Steve himself was concerned, saying, I don't know, Bob, this seems like a pretty esoteric topic for are you sure your audience wants this? And I told him, I'm not trying to be Taylor Swift. I'm going for Dan Fogelberg. All right. And if you don't even know who that is, good. That's my point. So real quickly here, I've had Steve on the podcast before, so I'll link to some of those other episodes if you want to check that out. But just in case you don't know who he is, Stephen Landsburg is a professor of economics at the University of Rochester, where students recently elected him Professor of the Year, although I don't know how recent that description was written. He's the author of The Armchair Economist, Fair Play, More Sex is Safer Sex, The Big Questions, those are all books, 2 textbooks in economics, a forthcoming textbook on general relativity and cosmology, and over 30 journal articles in mathematics, economics, and philosophy. His current research is in the area of quantum game theory. He writes the monthly Everyday Economics column in Slate magazine and has written regularly for Forbes and occasionally for the New York Times, the Wall Street Journal, and the Washington Post. He appeared as a commentator on the PBS/Turner Broadcasting series Damn Right, and has made over 200 appearances on radio and television broadcasts over the past few years. So one of my favorite economic commentators at his blog, The Big Questions. Whenever he posts something, I devour it and often disagree with Steve, but it's great just to go through the process. It helps sharpen my understanding of the issue at hand. Without further ado, here is Steve talking about his favorite mathematician. Take it away. Well, Steve, welcome back to the Bob Murphy Show.
Thank you. You're my favorite podcaster. It's always a pleasure to be here.
Oh, well, you're my favorite blogger. So there you go. So for the folks at home, this is, you're going to talk about your favorite mathematician. And I think we'll do some of the anecdotes of his life on the front end maybe, and then transition into more like his technical work for the true, math nerds in the audience. Does that make sense, Steve?
Sure.
Okay, so take it away. Who is this man of whom you speak?
Alexander Grothendieck was certainly the dominant mathematician of the second half of the 20th century. I would argue that you could make an excellent case for him being the greatest mathematician of all time.
But just so I understand, nobody would, or not nobody, but most people would say, oh yes, Steve's totally on firm ground for saying of the second half of the 20th century.
I cannot imagine a knowledgeable person disagreeing with that.
Okay.
I would think, my expectation, I have not done this, but my expectation is that if you took a poll of mathematicians, a clear majority would say he's among the top 5 of all time.
Okay. And the reason, I know it's funny, I'm stopping you like mid-sentence. You couldn't even get your first sentence out. I'm curious because I've only heard of him through you, whereas Gauss and Euler and Newton and Leibniz, and there's some big names that people have heard of, those famous mathematicians. I mean, some of them it's because they did other things besides math, But yeah, I'd never heard of the guy. Is that just, was I in a bubble, or is he not well known outside?
Probably because the work of Newton and Euler and Gauss has been around long enough that people have reworked it and made it simpler and made it simpler and made it simpler over centuries, to the point where we can now teach it to undergraduates. And the work of Grothendieck hasn't been around that long. I suspect that has a lot to do with it.
One last one, just to get your take. People know Einstein, though, and he's, relatively new.
That's true. I think, Einstein got a lot of mileage out of the bushy hair. And
I know, I think he's a smart guy.
And, things like he got good press. He got excellent press. I certainly would say that Grothendieck was comparable to Einstein among 20th century geniuses.
Okay, all right. So you're not screwing around. This guy is the real deal.
Yeah. To convey to your audience the content of the mathematics, and I understand you said we'll get to that later, but I want to say this up front.
Sure.
I cannot be completely accurate and still be comprehensible without a blackboard and 6 months. Right. So I'm going to tell lies, but I think that I will not do violence to the spirit of the truth. I will simplify. I will oversimplify. Right. I will speak a little vaguely, and I can imagine a mathematician watching this being a little annoyed with some of the simplifications I make, but I am going to do my best to convey at least the spirit of the truth, and not.
I'm going to be obnoxious and stop you again. People are like, Bob, let the guy talk. You brought him up because you reminded me. This is the exact thing that happened. I don't remember what I was doing that led me down this path. I don't know if I was teaching at the undergraduate level, or it may have been that I was writing, like a textbook called Lessons for the Young Economist. It was just supposed to teach introductory economics, and I was realizing like I was having trouble defining income. And you said, what do you mean? What are you, an idiot? And it was like, no, because it was intended for like 7th and 8th graders. And I was like, there's nothing, no matter what I write, it's either way too abstract, but more accurate, or it's comprehensible and intuitive and they're going to get what I mean, but it's wrong. And, and so I asked my brother, who was in a PhD math program at the time, so he would teach undergrad classes. And I said, when you're teaching kids math, do you like teach them wrong things? And he said, oh yeah, all the time. You can't avoid it. Or I said, do you teach them false things? And he said, yes, in the sense that there's certain things that, like, it's not, if they go further in it, there's more subtleties involved, and it's just kind of a, like leaving, there's more to the story than I can get to, but if I brought in that stuff, I just know I'm going to lose them. And so I'm teaching them, that kind of a thing. So I realized, like, even in math, to teach, people who aren't at your level, sometimes you got to say kind of, anyway, you get the idea what I'm trying to get across.
So maybe us jump directly to the most impressive part of Grothendieck's life. There are so many. I need to say a little bit about the math before I can talk about them. Just a little bit, and then more about the math can come later. But we know from Descartes that there's a lot to be learned about equations by drawing graphs of them. Descartes taught us that a quadratic equation can be represented by a parabola, or a linear equation can be represented by a line, and that studying the equations and studying the geometry feed into each other. The geometry tells us something about how to solve the equations. The equations tell us something about what the geometry is going to look like. And that was a fantastic discovery by Descartes hundreds of years ago. In the 20th century, in the roughly 1940s, another great 20th century mathematician named André Weil had the insight and the daring to suggest that there should be a similar sort of relationship where we're studying not just any solutions to equations, but in particular whole number solutions to equations. In other words, if you want to know what are all the solutions to some equation, y squared equals x cubed plus 7. You can draw a curve and you can say all of the solutions to that equation, they're in correspondence with the points on this curve. But if you're only interested in whole number solutions, looking at the curve doesn't help you. Now you're looking for points which have integer coordinates. And just looking at the curve, you can't tell which points have integer coordinates. And no matter how much you zoom in on that curve, you're never going to know whether a point has integer coordinates or whether the coordinates are just so close to integers that you can't see the difference. So looking at curves, if you're interested in all the real numbers that satisfy your equation, yeah, they're represented by that curve. If you're interested in all the whole numbers that satisfy that equation, in other words, if you're interested in arithmetic, just looking at the curve is not going to help you. But they had this amazing vision that the overall shape of the curve governs the number of integer points on the curve, or governs invariants that are related to the number of integer points on the curve. If you can count the number of holes in the curve, the number of times it twists around on itself, things like that, that gives you information about the number of integer points on the curve. And not just the number of integer points, but points of other. Suppose you're interested in points that are, you don't want to allow all real numbers. You just want all real numbers that are sums of an integer plus the square root of 2 or something like that. You can get information on all that stuff at once by looking at the geometry of the curve. And this was V's vision. And he proved some cases of it and then conjectured that this astonishing vision of how that should work in general. And it was immediately recognized as just a fantastic vision that we were probably 1,000 years away from being able to prove. Mm-hmm. And that was when Grothendieck...
Can I stop you real fast,
Sure.
Steve, just to make sure we're not losing? So like y equals x squared, for some people like it, like that. So you're saying like 0, 0 and -1, -1 and 1, 1 are examples of
those are points on that curve. Absolutely. Right. And it's very easy. If it's y squared equals x, or x, I forget which one you said. If it's x squared equals y, I know how to find points on that curve, integer points on that curve, 3, 9, 4, 16, and so on. Mm-hmm. If it's y squared equals x cubed plus 7, it's not immediately obvious how to start looking for integer points.
Okay.
And it's not immediately obvious from looking at the curve whether there are any integer points, or whether there are a finite number, or a large number, or a small number, or an infinite number.
Okay. I just wanted to clarify, you mean that for a two-dimensional curve that the x and y coordinate are both integers. That's what you're talking about?
That's what I mean. Yeah. That the x and y coordinate are both integers. Those are the points you're really interested in if you care about arithmetic. And again, they had this vision that, contrary to what any reasonable person I think might have expected at the time, that the shape of the curve gives you information about that in a very precise way. And that's where Grothendieck comes into the story. Okay. Grothendieck at age 30 had an incredible vision of how to prove this. His vision, he laid it out in tremendous detail in a talk in the late 1950s. And he basically said, here's what needs to be done. Here's what needs to be done next. Here's what needs to be done next. Here's what needs to be done next. It's going to take 10 or 12 years to do all of this. And at the age of 30, he announced this program and somehow attracted many of the world's best mathematicians, people like Mike Artin, who had tenure at MIT and was a top guy at MIT, left wherever they were and all came to Paris to sit at Grothendieck's feet for years, while he stood at a blackboard and gave his proof day after day after day for hours, filling in the detail, and everybody else basically sitting there, helping to fill in details, helping to fill in gaps, taking notes. Jean Dieudonné, who was one of the most prominent mathematicians in the world, would come in every morning at 5 a.m. to take all the notes from the day before and write them up in a coherent form and have them ready by 8 o'clock when Grothendieck came in. After 12 years of this, I want to say the problem was solved. It was almost solved, and it was pretty clear that Pierre Deline, a student of Grothendieck's, knew how to finish it. Mm-hmm. Grothendieck, he found Deline's method. Yeah, it solved the problem, but it wasn't pretty. It wasn't beautiful in the way that Grothendieck wanted it to be. And he was very, very upset about this. Possibly for that reason, possibly for other reasons. At that point in 1970, Grothendieck, 42 years old, left mathematics. And Deline finished off the proof, but finished off the proof using everything that Grothendieck had done for that intervening 12 years, using everything Grothendieck had done for 10 hours a day, 5, 6, 7 days a week for 12 years. It was just one of the most extraordinary accomplishments in the history of mathematics. And but that's the tip of the iceberg. Mm-hmm. What makes it so extraordinary was the philosophy behind it and the method. And let me illustrate this.
Well,
Sure.
Can we pump the brakes? I want to just unpack, because you're right. What you said there, I don't want the listeners like, oh, okay, that's impressive. Like, no, because you wrote a blog post on this years ago at this point, right? You called it The Generalist. This was in November 17th, 2014, when you're talking about that. And by the way, you say here, those who did know him tend to describe him as a man of indescribable charisma, with a Christ-like ability to inspire followers. I've heard it said that when it's Grothendieck, am I saying that right?
Yes.
Walked into a room, you might have had no idea who he was or what he did, but you definitely knew you wanted to devote your life to him. And so as you're saying there, like that, I mean, what's amazing about what you said is that, for one thing, like, was he paying these guys? Like, how did they?
Nope. I don't know. I actually don't know. There was a research institute outside of Paris that was created for Grothendieck. It was a lot of private funding was raised to create this institute where Grothendieck could stand and talk all day. Right. I don't know what the funding situation was for the people who came there. That maybe they were. Mm-hmm. I'm sure they were not. I'm sure they weren't getting rich.
Right.
But the institute had visitors, and presumably they paid their visitors, I guess, in the way that universities pay visiting scholars. I don't actually know.
Okay.
They were living on something.
Right. Well, because I mean, but they weren't mere stenographers. Like, it did matter that
these
it was
were not
some
stenographers. These were great mathematicians,
right? But I mean, but they
putting
were
their
helping
own
him.
research on hold, putting their own research on hold for years to be a part of it.
Yeah. So the thing that's just so audacious and bold and like almost reckless about this whole story is, like, if you had just said he saw it and he knew, like, oh, it'll take me this long to get through this proof, and then he just had people kind of just show up and just write down what he did. I mean, that would be unbelievable. But if you're saying he also kind of factored in, there's some things where it would be good if I had other people helping me get through it. And he anticipated all that and still was able, like, that's Absolutely. Incredible.
And the key person there, I should mention this name, was Jean-Pierre Serre, who was actually not one of the ones who sat there taking notes all day, but who Grothendieck consulted on almost a daily basis, and who had a fantastic amount of input into this project as well. And okay. It would be a travesty not to mention Serre's name, because I think without him it might never have happened.
Can I ask, just so we get, like, sure. Was there, again, because like all the people sitting there for that long, in that intensity too, it's not like they went in for a few hours and then went out to the pool. Like you're saying, they were going to work every day.
Yeah, and people came for a year, people came for 2 years. They weren't all there for 12 years.
But still, so were they publishing, like, intermediate things along the way,
Yes.
like so that they knew,
Yes.
okay, this is
There are
working and not
there are
just
20 volumes. There are 20
Okay.
volumes. And you know, the work fills these 20 volumes, and they were coming out in pieces all along the way.
okay. But still, but each was a necessary building block towards this. to
Each
solve-
was a necessary building block.
and just so we get the other guy, like he had made specific conjectures that they were
He
trying
had
to
made
prove.
very specific conjectures.
Okay.
There is so that so understates what happened though, because along the way, and I'll give some examples of this.
Yeah, sure.
Grothendieck found it necessary to completely change everything about the way we think about geometry. And I want to.
By the way, let me remove my constraint about let's do the biography and then the math, like because it's too impossible. Like just so, tell it how you think it needs to be told.
Okay. I'll start with this analogy, which I used in one of my blog posts, not the one you quoted, but a different one. Suppose you're a clockmaker, and you're a very oblivious kind of clockmaker. You haven't really noticed very much about the world around you. But one day you're working on a clock, and you accidentally drop the clock, and it falls to the floor. And you say, "Oh, that's weird. I wonder why that clock fell to the floor." So you take another clock and you try letting go of it, and you discover that one also falls to the floor. And you do that a couple times, and you just every time I take my hands off a clock, it falls to the floor. And then you say to yourself, I wonder what it is about clocks that makes them fall when you let go of them. So you start studying the internal mechanics of the clock. You start looking at the gears and the springs and trying to figure out what is it about all these gears and springs and things that make clocks fall when you drop them. And of course, you never solve the problem because you are so completely on the wrong track. They fall not because of anything internal to the clock. They fall not because of anything special about clocks. They fall because everything falls when you drop it. And if you step back and say, oh my God, this problem has nothing to do with clocks. It's that everything falls when you drop it. Now you're poised to discover the theory of gravity. In some sense, Grothendieck's entire vision was that all of geometry, everybody studying geometry was failing to step back enough. They were trying to understand why certain things happened in certain situations. And they were focused on the details of those situations. Whereas, in fact, to solve the problem, you had to start with the question, what are all the situations in which this thing happens? What's the most general form of the problem? Do it with math. Take a prime number, double it, and then halve it. You get the number back again. Start with 3, double it, you get 6, halve it, you get 3 back again. And then you say to yourself,
primes? Yeah.
What is this about primes? What's so special about primes? And you spend your whole life thinking about primes and what makes them do this. And you fail to solve the problem because you didn't ask yourself, are there any other numbers that this is true of? And when you discover that there are other numbers it's true of, that allows you to notice that there are actually some very simple reasons for this. So Grothendieck was, I called him once the Messiah of zooming out. He zoomed things out to a degree that was unprecedented in the history of mathematics. Anything he wanted to study. In fact, he compared himself to Serre, who I mentioned before, who was the other truly great mathematician of the time. Grothendieck always said, when there's a nut to be cracked, Serre will find the exact perfect chisel and insert it at the exact perfect spot and tap it with a hammer with the exact perfect force, and the nut will spring open. I will take the nut and I will submerge it in the ocean, and I'll leave it for months while the water wears it down, and then I'll take the nut out and I'll open it with my hand. It was all about submerging things in the ocean, seeing the great giant vision of what was going on. And that was why he was so upset at the end when Deligne put the last final step on solving the V conjectures, Deligne pulled out a chisel,
Okay.
which really annoyed him.
Can I, even on that point, can I ask you, was it, I mean, because it's standard, like somebody proves something one way and then somebody else comes up with a more elegant way to prove it. Like he was that mad, like he wanted it to not just be that the more general, elegant proof could be constructed, but he said we should have done that first. Like, I'm mad.
Yeah, he was opposed. No, he was opposed to chisels. I mean, he had great respect for Serre, who he said was the great chiseler, but he did not want problems solved by chisels. In fact, I had a friend who said this to me once, and I think it's absolutely true. He said the reason why Grothendieck stood so far above everybody else is that everybody else was trying to prove a theorem, whereas Grothendieck was trying to understand geometry.
Okay.
To Grothendieck, proving a theorem without having a full understanding of what made this theorem true made you a bad person. It was all about the depth of understanding. In fact, prior to all this, his first great discovery in his 20s, he's starting out his career. In his 20s, he proved this astonishing theorem, which is absolutely fundamental to geometry and is now called the Grothendieck-Riemann-Roch theorem because it built on work of other people. Grothendieck-Riemann-Roch is one of the central theorems of geometry. He proved it when he was like 25. His career is starting out. He refused to write it up because he felt like he had been clever. The proof was clever. Cleverness had no place in mathematics. It had to be about depth of understanding. He never wrote the paper.
How do we know about it?
He sent a letter to Serre, in fact, the same Serre I've mentioned before, and another guy named Borel, with an outline of the proof. And they spent months studying the proof. They had a seminar where they went through it and so on. They were incredibly excited about it. They kept pushing him to write it up. And he said, I'm never going to write it up. You guys write it up. And Borel and Serre eventually published a paper where they had this theorem and they gave full credit to, this is strictly the ideas.
That's what I meant to ask you a minute or 5 minutes ago at this point, that when he assembled at age 30, I was going to say, he published a bunch of stuff like for people to give up their positions and go live, you know what I mean? Not just his vision, but
he had done Grothendieck-Riemann-Roch, and briefly before that, he had worked in a completely unrelated field called functional analysis, where he essentially killed the field. His doctoral thesis in functional analysis basically killed off all of the interesting problems in the field.
Like, it's fair to say, with some rhetorical flourish, that the reason he moved on was because he solved that particular niche of mathematics with his doctoral thesis.
I think he actually said that at one point. There was just nothing more to do in the field, so
That's
he started looking for something else to do.
Okay.
And algebraic geometry is a much vaster field than functional analysis, so it was there was a lot more room to work. So where does that lead?
Well, let me just circle back. So I guess I understand it. If he spent this whole, was it more? Well, how long was it that
12
seminar?
years. It was 1958 to 1970, 12 years.
Okay, so if he's doing the 12 years and then right at the finish line, his student shoots up on steroids and then finishes, you could see why he would be so mad. Like, we just went through 12 years and now you're finishing it in this ugly way. What are you doing?
Right. And
Okay.
I will come to Grothendieck's autobiography, where he wrote very bitterly about this, that, I spent 12 years tending the orchard, and this guy comes along and picks the fruit.
Okay. Yeah. I guess I get it more now. All right.
But in accordance with that philosophy, the way he went about solving the V conjectures was to say, you guys, you're all looking at curves and planes, and you're like a clockmaker looking at clocks. when you need to step out. The things that you think are curves and planes, that's just a small subset of what curves and planes are really like. We have to, and points for that matter, we have to vastly generalize our notion of what a point is, for starters. What is a point? A point is a set where, I'll be a little bit technical here, but just it's a place where a function only takes one value. What's a function? A function is something where you have it turns every input into an output. Y equals x squared. That's a function. Right? And if you allow yourself to put in, if you're starting with a line representing the number line, you can put any x from that line into your function and you'll get out a y. If you don't start with a line, if you start with a point and you say that's the only thing I'm allowed to put into my function is that point. A point is a thing where if you restrict your functions that all the inputs have to come from that thing, then the outputs of those functions are only going to have one value because there's only one point to put in. There's only one. So, all right, that seems like a strange way to redefine what a point is, but it has deep implications because, first of all, what's a function? A function is something where I put in an input and it outputs a real number. Maybe it's something where I put in an input and it outputs a complex number. Or maybe it's something where I input a function, I input an input and it outputs a whole function. Those are different points. A point, you can say it's an input to any real valued function. Here's a different point, which is an input to any complex valued function. We want to think of those as different points. They're not the same. This is a point that you are allowed to define functions on, which must be real valued. And each of those functions has only one value. That's what this point is. Here's some other point where we're allowed to look at a different kind of function. So it's very important to distinguish those points from each other. It turns out that there's this vast array of different kinds of points. When we look at what we call the real line, every point on that line, we're usually thinking about real valued functions. So every point on that line, we're sort of thinking as something that we could put as an input to a real valued function. Okay, so those are all real points, but there are other points you don't see when you draw that line. There are points that are allowed to be inputs to complex valued functions, and they're not part of what we usually draw when we draw the real line, but they're there. And you really have to take account of them if you want to understand geometry. I realize that sounds incomprehensible. There are other kinds of points you don't see. Look at the plane. The plane is full of curves. It turns out, and Grothendieck made a compelling argument for why this is a very natural thing to think. I'm not sure I can convey that argument. But he said every one of those curves has associated with it what he called a generic point, which is infinitely close to every point on the curve. So take your plane, draw a circle in the plane. There is a point in that plane that is infinitely close to every point on the circle, even though those points are not infinitely close to each other. And that point is there. And if you ignore it, you're making geometry unnecessarily difficult. You need these points in order to make it possible to make simpler arguments. It sounds like you're complicating things.
Right.
But the great vision is that if you recognize you were looking at points, that's like looking at clocks. You should have been looking at all objects, and all objects include these other points that Grothendieck saw were there that nobody else had ever noticed before. And that
can I stop you just to make sure I'm getting the claim? So this the circle one. You know, somebody's a regular circle, like in the
regular circle in the plane
or northeast quadrant. Okay, and then you're saying Grothendieck is saying there exists a point that's infinitely close to every one of the points that we can see on the circle,
And
Is that
it
true?
lives in the plane. Yes.
Yes.
And it lives in the plane at a point that we do not normally draw. It's not one of the points that you
Okay,
normally
that's what I was going to clarify for people in case like, what are you talking about? He doesn't mean one of these points is infinitely close to all the other. That's not what he's saying.
No,
There's an invisible.
There's a point in the plane that you cannot draw because it doesn't.
Right.
It's impossible to draw, but it's there.
Just like if some clockmaker just kept dropping clocks, he would never realize dropping bowling balls. Also, you'd see stuff falling because if all he ever can see is clocks,
right,
he's not going to realize. Even though to understand gravity, you got to know about bowling balls too.
And it turns out that to understand elementary geometry at a level necessary to attack problems of arithmetic, you really need to acknowledge these other points and admit that they're there. I feel sure that I've mystified your audience entirely, but the vision was over and over again to introduce these completely new concepts of what a point is, completely new concept of what a line is, completely new concept of what a curve is, and recognize that once you get used to them, it actually makes all of geometry much simpler and makes it easier to prove. That's where you're immersing everything in the ocean and letting the water do its work. And somehow everything gets smoothed out. And every step in the proof should be obvious. I mean, this was really critical to his vision. There should never be a difficult step in a proof.
Okay.
The difficult part should be setting up the vision that makes everything easy. And then everything should just flow.
Okay, so is it like this? That was the guy's name V? Was that the guy who did the
Yeah.
conjectures? Okay, so he had a bunch of conjectures. Everyone knew. That's what I was going to ask you too. It would be important for people to prove those. Like it'd be
everyone knew it would be fundamentally important.
So, greatest mathematicians at the time are looking at it and like, "Geez, I have no idea how to prove that. Like it'd be awesome if we could, but that's going to take 1,000 years, like you said."
Everybody was saying that.
So then in Grothendieck, his strategy was, okay, let's just think about what's a point. And everyone's like, what are you talking about?
Exactly.
And why are we going down? No, the solution's got to be over here somewhere. We got to go build a super collider to attack it. And he's like, no. Let's just think about what a point is. And he just keeps walking. And they're like, okay.
You know,
and then it's step 24. And boom, we just proved that guy's conjecture. And you're like,
you start again. I am not being precise here, but in some sense, what happens is you look at the V conjectures, you start trying to prove them. And at some level you say, geez, if only there were more points in the plane, it would. I'm stuck because there are not enough points in the plane. Somehow at some point along the way, I get stuck because I don't have enough points to think about. And Grothendieck's solution to that is, well, then you must not be seeing all the points. There must be more points that you're not seeing. And then an
analogy occurred to me. Can I run? And if this is not analogous enough, and you want to say, nah, don't. That's not the way to think about it. You're not gonna hurt my feelings. But like I know, at one point, like or at least the claim is that the Pythagoreans didn't believe in irrational numbers. As far as you know, is that true?
Yes, that is
okay. So like if you were drawing a triangle, like you could have a 3, 4, 5 triangle, and but if you didn't believe there could be a length that was an irrational amount, that would kind of limit your ability to understand triangles.
Great analogy. Great analogy. All right,
good. All right, I got a pat on the back, gold star.
And so Grothendieck's position, if you can't tell the difference between a real and a complex point, if you don't see the generic points that are infinitely close to all the points on the various curves, you are blind in the same sense that the Pythagoreans were blind. Those points are there. And you've got to work out the consequences of that. And then somehow that's the hard part. Is getting all those foundations right. And once the foundations are right, the theorems should flow easily. Every step in every proof should be very simple.
Can I ask, in his, like when he kind of outlined the scope of here's what I'm going to do, gentlemen, was it all men or were some women involved?
Oh, good question. I do not, off the top of my head, I cannot think of any women who were seriously involved with this program at that time. I mean, I can certainly think of terrific women mathematicians who are in the Grothendieck tradition and who use his methods and use his work. But were there at the time during that crucial 12 years, I can't offhand think
Okay.
of one.
Not that I'm just saying
Yeah.
because I said gentleman
Yeah.
and I realized, oh, wait a minute, is that true? All right. So when he sketched it out and said, this is what I'm doing, who's with me. Do you know how specific, like, did he say basically, I'm going to redefine what a point is. And then once we do that, we're going to, okay.
Yep. Yeah.
Okay.
Yeah. Now, I was never in my life, I never saw him. I was never in a room with him, but I know a lot of people who were, and I know a lot of people who were there in the 60s when all this was going on. And I've known a lot of people who knew him since then. And they all say the same thing that you quoted before. It is astonishing to what extent they say it. They say the charisma was indescribable. That when he said, "Follow me," everybody in the room got up and said, "Yes, we're with you." It was partly the power of the mathematics and partly the power of the personality.
Well, it's funny, even this photo you have of him, he is like straight, he almost kind of looks like a Jean-Luc Picard or something. Like, yeah.
There are very few photos. There are very few photos. I am almost sure there is no video. There are a couple of audio tapes.
Was he French? Do I have that right?
I think he was stateless. I think he was technically stateless. He was probably not a whole lot.
What language was he lecturing in?
He lectured. French was the language he mostly used.
Okay.
I believe he was born in Germany. As a child, was shuffled off to France to avoid the Nazis. And lived kind of in hiding in France for most of his childhood, sometimes hiding out in the woods for a few days and sometimes in foster homes and so on. I am pretty sure that as an adult, he was never a citizen of any country.
Even cooler now. Is that worth expounding on? Like, why?
Well, first of all, I'm not 100% sure I'm right about that.
Okay.
I'm pretty sure I'm right. He was very passionately anti-authority of all kinds.
Now half my listeners are like, "What? Wait, what?"
Very passionately anti-authority.
Their attention perks up.
And in fact, his stated reason for leaving mathematics, they had in 1958, at the time when Grothendieck was starting this incredible project. The French government, together with a lot of private fundraising, created this institute. They built it around Grothendieck for this project to take place in. They made him I don't know, his title was full professor or something like that, and a couple of other people. But basically, the institute existed to support Grothendieck. In 1970, when he left mathematics, the reason that he left mathematics, and people have been skeptical about this, but his stated reason was that he had discovered that the institute was taking some of its funding from the military. And from there, he became an activist of some sort. He was an environmental activist. He was an anti-war activist. He had a general anti-all authority kind of vibe to him. I don't know whether he would have considered himself a libertarian. I don't know of his ever addressing issues of economics. I don't know how he would have felt about redistribution of wealth, for example. He was very concerned about limiting the sizes of militaries. He was very concerned about the environment. And there was a lot of naivete, I think, in a lot of his positions, but they were not positions that you or I would find morally reprehensible by any means, I don't think.
This raises an interesting question. So I know, like, Richard Feynman comes to mind, that, very iconic figure, and definitely, like, doesn't follow rules very well, but he's a genius, and he kind of gets by because he's so smart and productive that the authority figures are kind of like Feynman, and who is it, Bobby Fischer. There's lots of examples of these iconoclastic geniuses who don't like to be told what to do. Am I just focusing on a few examples and they stick with my mind because I think that's flamboyant and fun, or do you think there's something about
type? It's a personality type, right?
Yeah.
Grothendieck, I think, was with no slight on Feynman intent. Feynman was a brilliant guy, but Grothendieck was 50 times as smart as Feynman, and probably 100 times as smart as Bobby Fischer. He I don't know. I mean, again, the stated reason for leaving might or might not have been the real reason for leaving. I think it's clear he was having some kind of a mental or emotional breakdown at the time.
Right.
Because not thereafter, he moved to a tiny village in the Pyrenees and started raising goats. And for a long time, nobody knew where he was. Then he started doing mathematics again. And these 1,000-page manuscripts started suddenly appearing. Nobody knew where from. Nobody knew exactly where he was. But these manuscripts would appear. And
like under his name, they just didn't know where he was living? Okay.
Under his name. And a couple of those are major drivers of research in the field to this day, people trying to carry out the implications of the stuff he was doing at that time. So there was, he couldn't resist. He kept coming back and he kept saying, this is my last foray into mathematics. And then there kept being another one. He also wrote this remarkable autobiography, which I can come to in a few minutes.
Can I ask, was all of his work from that point forward still was it algebraic geometry? Is that
algebraic geometry mostly, but also an attempt to rewrite the foundations of topology, which is a related but different subject. And he was attempting to rewrite the foundations of topology in a way that was sort of as radical as the way he had rewritten the foundations of algebraic geometry. That has not panned out exactly the way he envisioned, probably, but there is so much there that people are worth. I mean, there is certainly a lot there worth pursuing, and a lot that has not yet been anywhere near fully plumbed the depths of. My friend Bob Thomason was a great topologist who he was one of the first people to receive one of these manuscripts from Grothendieck. And Bob studied it very carefully, and he wrote back.
So he just gets it like he's the first person on Earth to see it.
Yeah, came in the mail.
That must have been unreal. That must have been like a defining moment in his life.
And he spent a long time with it, and he wrote a letter to Grothendieck, and he said, there's a lot in here that is absolutely brilliant. There's a lot in here that other people have attempted before that you might not be aware of, and it didn't work out, and here's why it didn't work out. And here are some paths you're going down that, he said specifically, this person and this person and this person tried to go down that path, and here's why it failed. And again, you're probably not aware of that, but he also said, these other parts seem to me to be, thoroughly original and thoroughly brilliant. And he gave him a lot of detailed feedback. And he got back a one-line letter from Grothendieck that said, obviously, you're not the man I thought you were. I never wish to communicate with you again.
I just hope you and I, Steve, never have to send that email to each other. Wow.
By then there are many stories, and I don't know for sure which ones are true, but they apparently, there were a small number of people who, with great effort, found out where he was living and traveled to try to visit with him. And in some cases, he just refused to talk to them. And in others,
was he married, or he was just totally just him and his goats?
It's just him and his goats.
Okay.
He, according to people who saw him at that time, he was extremely concerned because he had realized that the speed of light is almost, but not exactly, 300,000 kilometers per second. And the fact that it could be that close and not exact must mean that it used to be exactly 300,000 kilometers a second, and the devil had changed it. And this was extremely alarming because it meant that the power of the devil was growing.
Okay.
So, I think it's fair to say that if that's an accurate story, and I believe it's probably accurate. I don't know for sure, but I believe it's probably accurate. That probably his mind was not entirely working.
For one thing, the devil uses qubits. So.
And for another thing, I mean, kilometers are a completely arbitrary unit of measure. The unit you could make the speed of light anything you want by choosing a different length measurement. So, and the autobiography is full of strange stuff like that. He has a very, very long part on proving God exists. You'll like this. Here is, and I believe this is an accurate presentation. Now, his argument is so long and complicated, I might not be doing it justice, but I'm pretty sure this is the whole argument. A, we all have dreams. B, nobody can deny that we all have dreams. C, the only possible explanation of dreams is that they're messages from God. D, if there are messages, there must be a messenger. Therefore, God exists. I find that unconvincing, and I think most people would find it unconvincing, even people who agree with the conclusion.
Well, in fairness, though, it's the argument's valid. It's just I don't see how he would prove like step 3.
Yeah, that I think is where that I think is exactly where the weak link in the chain lies.
Right. But I'm just saying, like, but on the other hand, if somebody said, well, I'm going to redefine what a point is and then do that, you might say, well, if you could do that, sure, but you're not going to be able to.
All this stuff probably came to him the same way his mathematics came to him, and that had worked out pretty well for him. So he trusted it.
Do you know that's exactly what John Nash said?
Yes, I do. I do.
Okay.
I do. I should have given credit there.
Let me just, for the folks at home, let me just tell that just so they get the anecdote or the reference. John Nash, A Beautiful Mind, the Russell Crowe movie. I'm horrified, stupefied, terrified of you. That one. And by the way, I have to say this, Steve. The scene, folks, where he is in the bar and talking about Adam Smith was wrong. That is the opposite of what a Nash equilibrium is. Like the movie, it's not just it was a little bit wrong. It taught you the exact opposite of what John Nash did.
I absolutely endorse. I endorse that statement.
So anyway, but in the was it Sylvia Nassar who did the book The Beautiful Mind that the movie was based on? Anyway, that somebody asked him once because he was apparently going into I forget where do you remember where he taught Nash?
Princeton.
Was it Princeton? Okay, he would go into the faculty lounge and throw the New York Times on the coffee table, and they'd all be sitting around. And he'd go, "Yeah, you see that headline right there?" And they go, "Yeah." And he's like, "That's aliens communicating with me." And they laughed, thinking he was kidding, and apparently he was serious. And so later, people asked him "Geez, John, you're an intelligent guy. Didn't you realize some of the stuff you were dabbling in was kind of out there?" And he said just what you said, Steve. That he said, "Well, the same method by which I came up with these things that you're telling me I'm a paranoid schizophrenic is also how I did the things that you gave me a Nobel Prize for." So, I'm paraphrasing, but that's basically what he said. So, no, it wasn't clear to me. Yeah, I knew I was reaching conclusions other people would disagree with, but I also had found conclusions in math that nobody had discovered before. So,
Interesting to mention Nash, because Nash was in many ways the exact anti-Grothendieck in the sense that every argument he made was based on coming in with the chisel and the cleverness and finding the exact place to strike and solve the problem. Never that generalizing, zooming out kind of thing that you saw with Grothendieck. His autobiography is full of this weird stuff. It's also full of philosophy of mathematics and talking about his methods of generalization. We haven't even gotten to Topos theory yet, which I have to mention. But before we do, I just, this is a little long, and I want, maybe you can edit this down for your listeners if you want. It's a few paragraphs, but I took this from his autobiography. I think it really shows you how he thought of himself.
Okay, yeah, this is great.
Do you mind if I read?
No, go ahead.
Most mathematicians, this is Grothendieck talking, most mathematicians take refuge within a specific conceptual framework, a universe that's been fixed for all time. Basically, they encounter ready-made at the time when they do their studies. They may be compared to the heirs of a beautiful, capacious mansion where all the installations and interior decorating have already been done, with its living rooms, its kitchens, its studio, its cookery, its cutlery, with everything one needs to make or cook whatever one wishes. How the mansion was constructed laboriously over generations, and how or why this or that tool was invented, as opposed to why other tools were not invented, why the rooms are disposed in this fashion and not some other fashion. Those are the kind of questions that most mathematicians don't ask. They don't dream of asking. They have their universe. It's given once for all. It's impressive by virtue of its greatness, and at the same time, its familiarity and its immutability. When they concern themselves with it at all, it's to maintain or embellish their inheritance. They strengthen the rickety legs on a piece of furniture. They fix up the appearance of a facade. They replace the parts of some instrument. Even sometimes they go into the workshop and they make a brand new piece of furniture. Much more infrequently, one of them dreams of modifying one of the tools themselves, or even making a new tool. And once this is done, they make all sorts of apologies, like a pious genuflection to traditional family values. The windows and the blinds are all closed in most parts of this mansion, et cetera, et cetera, et cetera. And then, so I'm skipping a bunch here, but I consider myself to be in the small, distinguished line of mathematicians whose spontaneous and joyful vocation it has been to ceaselessly build new mansions from the ground. We are the sort who along the way cannot be prevented from fashioning as needed all of the tools, cutlery, furnishing, and instruments used in building the new mansion, right from the foundations up to the rooftops, leaving enough room to install future kitchens and future workshops, whatever's needed to make it habitable and comfortable. Once everything's been set in place, down to the gutters and the footstools, we aren't the kind to hang around. Although every stone and every rafter carries the stamp of the hand that conceived it and put it in its place. So that was how he saw himself, and I think
Okay. So that's how he's
accurate.
thinking, and his disciple comes along, and then at the last minute,
Yeah,
ships in something from the previous mason to just hang up on the wall or whatever. I can see, why he was so horrified by that.
but that leads the talk of building a mansion and then moving on and building the next mansion. There's that too, because you build up all of what's called scheme theory, which is where you're adding all these extra points and so forth. Again, my account of it will never hold up to a mathematician listening for technical accuracy, but I hope I gave you a little bit of the picture of scheme theory. And then you go on from there and you basically transcend scheme theory to this whole new vision, where now a point is no longer a place where you define functions, but a point is essentially the foundation of an entire mathematical universe. The whole mathematical universe that we normally study, sets, all of set theory and everything we build out of set theory, he views that as all supported by a single point. And then there are other points that support other mathematical universes where all the laws are different. Often the laws of logic are different. And what's a curve? A curve is something that passes through many different points. So a curve is something where you can travel along this curve, and as you travel along the curve, all the laws of mathematics change. If you stand here on the curve, then you've got maybe classical mathematics with classical logic. You move a little farther along the curve, you get to a place where the law of excluded middle doesn't hold, where you can't say that every statement is either true or false, that there are intermediate truth values. You move farther along the curve, and the sets there can be places along the curve where the elements of a set change. You've got a set in classical mathematics. That set has elements. The elements of that set never change. You could move along your curve and come to a place where that set contains different elements that it didn't used to contain before. The entire mathematical universe changes as you move along a geometric object. And in some sense, what is the geometric object? Fundamentally, that's not what's fundamental. What's fundamental is this vast array of universes. And the geometric object is the foundation that underlies them. And it turns out that this is a spectacular idea, not just because it gives you all these other universes to explore, which is amazing on its own, but because it ends up giving you fundamental insights into the geometry of curves. You end up being able to prove new things about curves you couldn't before when you realize that they underlie these vast mathematical universes. So there's your theory of toposes, which transcends the theory of schemes we talked about before. And then you go beyond that to what he called the theory of motives. He would complete the mansion and he would move on to the new mansion. Each one just more spectacular than the last. And every one of them, a major object of study in mathematics now as we're more than 50 years later. These are the fundamental building blocks of algebraic geometry, and algebraic geometry is very much at the center of pure mathematics in a way that I think it was not before Grothendieck. A very large number of fields in mathematics draw on algebraic geometry in a way that makes it, I would argue, the most central field in mathematics. It's the most widely used in other fields of mathematics. And it's all these fantastic, and that's because it's so powerful. We can prove so much. And all of that comes out of the methods we got from this guy.
Okay. Can I ask, just to explain the specifics of that metaphor of the building the mansions, is it when you say or when he says, oh, I built one and then I moved on to build another one, is it that he revamped the underpinnings of the first thing he did, or no, you got what I mean? Like you said, the theory of schemes and then toposes. Is it that the toposes even kind of revolutionized the first thing, or those are totally separate things?
They are, in some sense, totally separate things, in the sense that scheme theory is still a major part of mathematics. Topos theory did not supersede it. But topos theory gives you a different way of doing geometry, which is related to scheme theory, but it is different. And it gives you a whole new set of techniques and a whole new set of methods, and you can play them off against each other. So yeah, I guess that's my answer.
So I guess, was he revolutionizing himself or not? No, he just kept sequentially tackling different things. That's what I'm trying in the way, like Wittgenstein, again, this is way out of my pay grade. Wittgenstein does one thing and then it's oh, okay, that's amazing. And he's like, on second thought, this is actually what's going on.
No, this was not on second thought. I don't think he ever renounced scheme theory. He never thought scheme theory was a mistake, and it clearly was not a mistake. I mean, it solved the V conjectures. Right. Scheme theory was clearly not a mistake. Topos theory was built for other purposes. It was like, scheme theory is great. It solves all these problems for us. There are some problems it doesn't solve. Now let's create another theory that solves those problems.
Is the topos theory, is that the stuff that he wrote to the guy and then said, I'm not talking to you again? Or is that something else?
Topos theory actually was largely laid out during the 12 years that he was working on the V conjectures.
Okay. All right.
Some of that came later. Some of the later stuff was different.
Okay. Can you give us a little more? Again, I know you're threading it's a fine line. Like, you can be more accurate and specific, but then you lose more people. So I get it. But
I just want to say, looking back over the things I've said in the last hour, I hope no mathematicians watch this. It's full of lies. Again, I think it is accurately conveying the spirit.
Okay.
But there is so much that I have deliberately misstated in order to make it comprehensive.
Fair enough. So can you just unpack, and again, to tiptoe closer towards the real, at the accuracy at the expense of general understanding, when you were saying the thing where he wrote that massive thing to the guy who got it and then was going through it and then said, oh, I see what you're trying to do on this portion of your manuscript, but so and so 3 years ago published this result, and so that shows this is a cul-de-sac. And
Right.
Can you just give it like? I think that might be tricky for people because for the in the public's mind, like, well, no, the one good thing we can say about math is you prove something and it's true, or you haven't proven it, and so you don't know that it's true, but that's kind of an open and shut thing. Did you prove it or not? And so what do you mean? Like this is an unfruitful avenue to go. Like,
I mean, the Grothendieck view was proving stuff is not interesting. Understanding stuff is interesting.
Mm-hmm.
And if you have a clever proof where you can prove something great and you prove it by using a little trick that does not actually advance your understanding, that's of little value. Again, this is why he did not write up the Grothendieck-Riemann-Roch theorem.
Mm-hmm. Okay, let me put it this way. Can you give an example, or at least the flavor of what does it mean to say, like, he thought, oh yeah, I think this is a fruitful thing for me to spend the next few months on, and this guy's trying to give him advice. No, I know you've been living with goats, so you don't realize so-and-so published this result, so that means...
Right.
Can you just explain a little bit about that?
I don't... If you're asking me to... I'm not sure what you're... If you're asking me to say what was going on in Grothendieck's mind, I don't know any better than you do.
Okay. Here's what I'm... Okay. Did Grothendieck think, oh, if I go down this path with my understanding immersing the nut in the ocean, I bet you within 12 months, I'm going to be able to show such and such. And this guy said, no, this other guy proved that is not true.
I think that's quite possibly the way Grothendieck saw it.
Okay.
I find it plausible that that's the way Grothendieck saw it.
Which, if it were something, or at least so that was some of the example, you would think, how could Grothendieck possibly get mad at the guy? Like, no, if somebody's demonstrated that this is a dead end, then he's saving me. Like, again, who knows? But do you know? Like, could it be more that he's the kind of guy that would have just wanted to, like, no, if you were a kindred spirit, you would let me learn that on my own as I went through this, and then it would be obvious 12 months from now, like, oh yes, now I totally see why. Of course, that's not the resolution of this, because of whereas this other guy just proved it, and so now it's kind of like taking the fun out of it. And well, now I don't feel like putting the nut in the ocean for 12 months. I'm making stuff up, but do you understand what I'm trying to?
Yeah, it all sounds plausible.
Okay, that's good. Okay, Steve, I have one question, if you could elaborate on. Earlier, you had said how his contributions in algebraic geometry were very impactful. I don't even like that word. You didn't use it. Partly because it's so powerful in other areas. Can you just give an idea for people, like, what math is like, numbers and stuff? And I kind of remember, I guess, geometry. Like, when you talk about different areas of math, can you just like list 4 areas, let's say, just so people understand what do you even mean different areas, and what would it mean for one group of mathematicians who work in this area to borrow a result from over here?
Okay, a fair question. The whole motivation for this entire program, again, is the V conjectures, which relate arithmetic to geometry, and I'm guessing that most of your readers have a sense that arithmetic and geometry are not the same thing.
Right, but they're both part of math. Yeah.
Although the great insight of V was that geometry ought to be able to tell you a lot more about arithmetic than you think it does, and vice versa. And that's what that's the big motivation behind Grothendieck's work. So those are 2 areas of mathematics. There is there's topology. I'm not, which is also the study of geometric objects, but by very different kinds of techniques than one uses in geometry. Although there again, I mean, the whole field of topology, which is in some sense a very different subject than geometry, those guys have adopted Grothendieck's methods to a tremendous extent. Algebra, pure algebra, is now algebra means working with equations, means saying things like If I have a set of 6 equations and 7 unknowns, how do I tell whether there's a solution to those to that family of equations? Are there 7 values for the unknowns that satisfy all 6 equations at once? Algebra is completely suffused with. You would never attack a question like that now without first translating it into a question of geometry and then using basically Grothendieck's methods to study that geometry. I don't know whether I've come anywhere close to answering your question or not.
No, I mean that's for people who don't know what topology is. Like, can you give us what's a standard thing you would study in topology? Like if algebra is y equals x squared, okay.
All right.
Regular geometry is like a circle or something. Okay.
All right. I'll give you a question in geometry and a question in topology.
That would help.
I don't know if that will be sufficiently illustrative. Here's a geometry question. Imagine a surface in space. I mean, a very wavy surface. It's got hills, it's got valleys, etc. And imagine a second surface in space. And these are imaginary surfaces, so they're able to pass right through each other. Look at the place where the surfaces cross each other. That's going to be some kind of curve. For example, if one surface is a flat plane like this, there you can see my hand, and the other surface is a flat plane like this that comes at a different angle. You look where they cross each other, that'll be a line where those two planes cross. If this plane has hills and valleys in it, and this one has hills and valleys in it, there where they cross, you'll get a curve. Here's a geometry question. Start with a curve. Can you find 2 surfaces that cross exactly along that curve? That's a geometry question.
Okay.
Here's a topology question. Take a sphere, and this is an imaginary sphere, so if you push and pull on it, you can push it right through itself. Suppose you want to turn this sphere inside out. Well, here's what I would do. I would reach through the sphere and grab the far hemisphere, and I would grab each hemisphere, and I would pull them through each other, and I could turn the sphere inside out. At some point along the way, that sphere is going to crease. Question: can I turn the sphere inside out? If I'm a little more careful, can I do it in a way so that it never creases along the way? That was, for reasons I'm not sure I can explain, a very important question in topology for a very long time. It was remarkably solved after many decades of people trying by a blind mathematician who, I don't know whether his blindness was an asset to him or not, but it's the kind of question where you would think you'd have to really visualize what's going on. And
what was the answer?
The answer is yes, you can do it. It's very complicated. If you go to YouTube, I think you can probably find videos of people doing it. But it's a very complicated set of twists and turns.
I mean, does it mean like what it sounds like? Or is it like, well, yeah, I couldn't do it with a beach ball, duh, but we're talking about, you know what I mean? Like,
yeah, it's an imaginary beach ball
but I mean,
can pass
what
through
I'm asking? Like, it certainly seems like, well, how could you do that without creasing something? But
yeah, no, it seems very hard, and for a long time, I think many people suspected there was no way to do it. So it's kind of surprising that there is a way to do it. And
but here's the distinction. But you know how sometimes like you see the rings that are attached, and then it turns out, oh, wait a minute, if you do it like this, you actually can. Is it like that, like with the beach ball? Like, no, you really could, or is it no? There's a difference between it being physical matter versus the math.
Well, the thing about physical matter is you wouldn't be able to pull it right through itself.
Right.
But that's the only important way in which this differs from physical matter. Aside from that, yes, you're imagining an actual beach ball that can be pulled through itself.
Okay, all right. I will look up the YouTube.
And again, I think the guy's name is, I hope I have it right, Bernard Morin, I believe. Let me double check that. It's terrible that I'm not sure of this. I just started to Google and I almost moved away from our session here. That wouldn't have been good. Bernard Morin, yeah. That was his name. He was blind. He solved the problem. And yeah, if you go to YouTube, you will find they're a little hard to follow because it's this complicated series of moves. But you will find videos of people turning spheres inside out this way.
How do you spell his name?
Morin.
Okay. All right, folks. We'll link to that too, just to if you want to see that. Okay. So another question that occurred to me was, you were saying how Grothendieck. Am I saying his name right again?
Grothendieck.
He really wanted to understand something, and he didn't like just proving something out of cleverness. So I'm thinking you would appreciate that, because I've noticed that, like, in certain economics issues, like if Paul Krugman says something, or Stephanie Kelton, the MMT hero, if she says something that I just know is wrong, but I might walk around for a few days trying to really put my finger on what's so wrong about it. You know what I mean? And it's not enough if I can just demonstrate, to another economist or somebody, like, clearly this can't be right? Because if what they were saying is right, it would mean this, and we know that's not true. So they must be right. But no, I want to, like, really get it under the hood, like really understand it, so it's so obvious what their mistake was, or what the fallacy was that they were doing. And so I guess I can appreciate, like, do you try to do that in economics?
Yeah, I think it's a slightly different phenomenon, because when we look at something like the V conjectures as solved by Grothendieck's student Deline, Grothendieck's not saying I know that's wrong. He's saying I know it's right.
Right.
I just I just think that I don't understand why it's true.
So
I don't care if it's true. I want to know the real fundamental reason why it's true.
Okay.
And the real fundamental reason is not allowed to be complicated. It's not allowed to be complicated. It's got to be, the only kind of explanation he wants to accept is, we never saw this before because we didn't really understand what a point was. And if you redefine a point in the right way, then it's obvious. He wants an explanation along those lines, and any other explanation, he totally admits it's a valid proof. He totally admits it's true. So it's a little different than the phenomenon you're talking about. But he says it's a bad thing to care about that.
Okay. But what I'm trying to prove is true is that Paul Krugman's argument here is silly.
Yeah.
See? So that's what I'm saying. So I could prove it, and like you say, yeah, Bob's got it, but if we don't really understand the underlying subject more,
underlying
it should just be, and it should be obvious, like, oh yeah, that's what Krugman was doing.
Right. No, exactly. So you could say, Krugman made this 10-step argument here, and here in equation number 5, this doesn't make sense to me. But and then I'm going to say, but I want to know what the fundamental misconception was. I don't want to know where the mistake was in the.
I think you said in your the armchair economy, when you paraphrase David Friedman's Iowa car crop example, I think that's a good, like, to get across the idea of free trade to people.
Absolutely.
And there could be different. You could do all kinds of stuff, but his little thought experiment there is just like boom.
That's a perfect example. Yeah. Okay. No, I draw graphs on the blackboard to prove to my students that free trade is good, and I try to explain to them what those graphs mean. But there's no substitute for a simple example. And I don't know. I assume most of your listeners, or many of your listeners, will be familiar with it. But David Friedman's Iowa car crop example renders all those diagrams practically unnecessary.
Can you do it off the top of your head?
Sure, absolutely.
Yeah, that'd be good.
What David argues, and I'm sure others have made the same argument or similar ones, but I first heard it from David Friedman and opened my eyes. What he said was that we have two different technologies for producing cars in this country. We have the technology we use in Detroit, where cars come off assembly lines, and we have the technology we use in Iowa, where we plant corn in the ground. We take that corn, we load it onto ships, we send the ships to Japan, and the ships come back with cars on them. Some people say that one of those is a manufacturing technology and the other is trade, and that those things are very different, but they're both ways of taking raw materials and turning them into cars. And if you think that if you think it is bad to produce cars through one of those methods just because it's not the method you first thought of, well, what are you saying? Are you saying that the only good way to produce cars is the way they're produced in Detroit, that we shouldn't look for new technologies? All trade is a new technology. A trading partner, just think of them as a machine. You put one thing into it and a different thing comes out of it. And when you see it that way, I mean, then you see that, okay, maybe you're a person who opposes technological progress, and then you can consistently oppose trade. But if you like technological progress, you got to like trade, because it is technological progress. It's just the discovery of a new way to turn inputs into outputs.
Yeah, yeah. So that's great. So again, folks, just to make sure you're getting the connection that I'm seeing there, that just, yeah, there's all kinds of ways you could prove that when we say free trade is good, you know, that we have specific things in mind that are rigorous. We don't just mean like, oh, I like it. And, you know, we could be specific about that. And you can do that with the blackboard. You can come up with examples of, let's suppose the country's making, you know, two goods in this other country. And even if it has the absolute advantage in both, look what we should, but still, for some people, it just, that might not be hitting them over the head. Whereas with Friedman's example, if you just think about it a different way and kind of broaden your horizon, then all of a sudden, you know, it's obvious. So that was the connection that I was seeing there. Is there like another set of results mathematically that you think would be worth?
There are, but I think it would be, as I think over the options, I think I would have to be even more inaccurate with those than I have been so far, and I think I'm up against the limit of my willingness to
your own personal
to
moral
things.
code of devotion to the truth is flashing warning. Okay, well, what about his? Okay, let's put it this way. So, when you rank him earlier, I'm just curious of how you evaluate these things. You had been saying, oh, he's, would you say 50 times smarter than Feynman and 100 times smarter than Bobby Fischer? Is that what you said?
I did say that. Yes.
Something like that. Okay. So I'm just curious, how do you, like, do you think mathematicians are there's a popular notion that, oh, the physicists are the smartest and the mathematicians are second in line and the economists are way down there. But at least we're better than those sociologists.
There are very smart people in all fields, and
okay.
you know, they're the. I actually think I find Paul Krugman's ways of arguing deplorable in many cases, and I'm not convinced of his honesty in all cases. But he's an incredibly smart guy.
Oh yeah, and I've said that too, by the way. When people say he's stupid, when people say Krugman's stupid, I say no, he's not, and you shouldn't be thinking. Even if he's your enemy, like, you need to know your enemy. Like, if you're walking around thinking he's an idiot, that's not correct. Like, I do say that. So go ahead.
Larry Summers, Bob Lucas was amazingly smart, and I remember Lucas saying to me that whenever he was in a room with Gary Becker and Milton Friedman, he felt like an idiot by comparison. So yeah, there are very smart economists, and I'm sure you and I have met many of them. There are very smart mathematicians and physicists, and I am less competent to judge the physicists than I am to judge the mathematicians. So take all this with a grain of salt. But if I were ranking 20th century physicists, Feynman would certainly be in the top 50. I don't think he'd be in the top 10.
Okay.
Grothendieck would surely be my number one among mathematicians.
Okay. And then I'm just curious, like, to me too, there seems to be an interplay. Like, it's one thing to know a lot, but like to also like if I'm going to call someone a genius, there has to be like creativity involved. That they're doing new things. It's not just so.
Yeah, and I mean, there's also raw intelligence. I mean, I never met von Neumann, of course. He was dead before I was born. But by all accounts, he was, by many definitions of intelligence, he was the most intelligent person that anybody is aware has ever lived.
Really? You've heard that?
Oh, yeah, repeatedly. People were astonished by his quickness and his intelligence. He just saw things instantly that took other people months to understand. In fact, somebody once told me that von Neumann was famous for getting along with everybody and treating them as equals, including toddlers. You put von Neumann down with a 3-year-old, and they would be talking as equals in no time. And the person who told me this, his explanation for it was, to von Neumann, there was no difference between a 3-year-old and everybody else he met. So there was no reason to treat him any
Right. So
differently.
he just had to decide: am I going to be nice to these humans, or am I just going to be disgusted about how dumb they are? Yeah, we're like little puppies or something. Okay.
Yeah, no, the stories about von Neumann's quickness and his ability to see the answers to things, not always to be able to explain the
Right.
answers, but his ability to see through to the answers to things, which took everybody else a year to understand. There's
Do you
story
know-
after story with those.
I want to say this anecdote. Tell me if you can independently confirm this. I know for sure Kurt Gödel, when he was at a conference and presenting what later we would call Gödel's incompleteness theorem, or I don't know if it was plural at the time, that he presented at a conference, and that it's so much people did not get what he just did that later they didn't even write it up in the summary of what was presented at that conference. Like, they didn't feel. And then there was one guy though in the audience who saw that and went up to him after to ask him, like, because he realized, whoa, there's something here. And I think that was von Neumann.
It was von Neumann.
Okay, so you know that. Okay,
It was von Neumann, and in fact, Gödel had 2 incompleteness theorems that are closely related, and now are usually presented as one big theorem. But Gödel had presented the first theorem there.
Okay.
Von Neumann was the one guy who really understood it. Von Neumann went home, proved the second theorem, and then learned that Gödel had also proved it, like within a day of each other, and von Neumann chose not to publish his. So he was actually, I don't know if he was an hour ahead of Gödel or an hour behind Gödel, but the second incompleteness theorem he did get independently.
And that kind of buttresses your claim that this was a pretty sharp fellow.
It's also, von Neumann worked a lot in pure mathematics, and not in areas that are among my main interests. So I'm a little out of my depth here. But people who work in that field have told me that when you read von Neumann's mathematical papers, you feel like they would be so much better if he just had 10 fewer points IQ, because everything was so obvious to him that he had no need to think more deeply about things. He was so good at finding the trick that would get you the answer to any problem. He never had to do what Grothendieck did and step back and try to understand things more deeply. He never needed to understand things more deeply, because whatever tools he had, he found a way to use them and get the answer to the question at hand. And then he stopped there. Okay. And if it had been harder for him, he would have had to think more deeply, and he would have discovered more things.
That's an interesting perspective. Okay. I mean, I don't know if I'm abusing the analogy too much, but so he teamed up with Morgenstern and famously, wrote the Bible on zero-sum games, and we get things like the von Neumann-Morgenstern utility function out of that. And then Nash came along and sort of generalized it. And so when I look at some of those results of what von Neumann and Morgenstern, people say that Morgenstern was more given the economic intuition and von Neumann was doing the math and all of their joint stuff.
That's what one always hears.
Yeah, that it does look like it's very specific. The reason I'm bringing it up, Steve, because it kind of dovetails with what you just said. That rings true to me when I was reading when they went to attack games. It looked like he wasn't trying to do a big, broad thing. It was more just oh, you want to know how to solve this game? Well, you could do this.
He wanted to solve problems, and whatever got him to the end, he was done, and then it was on to the next thing.
Right. Whereas you might have thought let's consider the class of strategic interactions.
Yeah.
No, we said we were going to solve a card game. Well, it's a zero sum, and here's how you would solve zero sum games. Boom.
And again, if he had been a little less smart, he might not have seen that quick solution, and he might have been forced to do a little more. Okay.
Is there? So I guess another question that occurred to me. So you said, they're going through this 12-year odyssey. right as they near the finish line, his student pulls out the chisel to get it over the finish line. Did anybody ever like do it the quote right way?
People are still trying to do it, to fill that final step using Grothendieck's original vision. He had outlined what the vision was, and it requires yet another complete revision of the way we view geometry. It's what Grothendieck called the theory of motives, and basically motives are kind of the atoms out of which geometric objects are built. Like a curve, you think of a curve as made of points, but it's not really, just knowing the points doesn't tell you what the curve looks like, because I can take a line, or I can take a parabola that's I can take, let's say, a cusp, a curve with a sharp point on it somewhere.
Mm-hmm.
They've got the same points. They've both got an infinite number of points. Just looking at the individual points, you can't tell them apart. Mm-hmm. But somehow there are, I'll call them atoms that these curves are made out of, which Grothendieck called motives, and they have the same points, but they have different motives, holding those points together. And the idea was that every curve is made out of motives. Motives are very simple. And if we understand motives, and then if you want to understand a curve, you just ask yourself, what motives is this curve made out of? I understand all those motives. Now I understand the curve. But the question is, what exactly is a motive? What is the definition of a motive? And that has been a huge part of the research program in algebraic geometry. If you could figure out what a motive is, you could complete the proof of the V conjectures according to Grothendieck's original vision. Tremendous progress has been made on that. We're not quite there yet.
Okay. And I guess your thought is that he was right, that vision, it will lead.
Oh, yeah. No, it's the nature of the progress that's being made suggests that we're going to get there.
Okay. I guess the last thing I'll say is when you took our break there, I was looking at your blog post, and the picture of him near the end of his life, it looks like an old Jedi Knight at that point. So he's a very interesting character, to be sure. Well, is there anything, I think we've reached a natural conclusion. Is there any final thing that you want to say?
I think my suspicion is that we've lost a very large part of your audience, because for better or worse, most people are not intrinsically interested in the history of mathematics, which is fine. We all have different interests. So I hope that there are a couple people still with us, and I hope that those people do not include people who know enough math to know how much I lied.
Well, they probably want to stick around to hear how to get in touch with you, to give you a piece of their mind. Joking aside, like, do you know, for somebody who wanted to know more of is there something they could go read that?
I had 2 blog posts about him in the week when he died. One of which you pulled up, the one you're referring to. And at the end of that blog post, there is a link to a page. I think it's landsburg.com/Grothendieck, where I have posted some articles about him. I am afraid they all assume more mathematical knowledge than your typical listener is likely to have.
Well, no, but this conversation I think was supposed to be the intermediate, and then for people who know enough math to like really want to get into the weeds.
Those people probably are already in the weeds.
Because it's like saying, oh, if you like physics, let me tell you about this guy Isaac Newton.
But on the other hand, there may be people who are totally up to speed on the mathematics, but a little hazy on the history, and they might be interested in reading some of this stuff. It is. Maybe it's Landsburg. It's Landsburg.com/Grothendieck. And the link is there in the blog post. And there are a bunch of articles there. There are some writings of Grothendieck, and there are some writings about Grothendieck. I particularly recommend the one by Colin McClarty, which I think is very insightful. There are 2 by Pierre Cartier, and I think the second one is a lot more worth reading than the first.
Okay.
But the McClarty one and the second Cartier one I would certainly recommend.
Okay, well, great. Do you want to plug like your website, like where people can go, or things you've got going on?
You can go to my site at thebigquestions.com, but I think, as Bob probably knows, I hardly blog at all anymore. So there's not, but there's a whole big backlog there full of stuff that I still think is as good as it was when I wrote it, which in some cases is very good and in some cases is not. So there's a big backlog of stuff there. There's economics, there's math, there's mathematical history, there's mathematical philosophy. That's a good place to poke around. And I keep thinking maybe I'll start blogging more regularly again sometime soon too.
Okay. Well, no pressure, but yeah, like I say, your posts are it's always a fun day. Like, oh, Steve posted. Great. So, well, thank you for your time and your insights and sharing.
Thank you. I told you before we did this, I have an infinite appetite for talking about this stuff, but and it's nice to have an audience, even if an audience of one. And I appreciate the opportunity, and I trust that any of your audience for whom this was not their cup of tea, they'll just come back and see what you do next.
Yeah, I think they'll give me a pass on this one. Everyone's allowed to Landsburg once in a while. I'm going to repeat what I have said every time I've been on your podcast before. You are the great podcaster. You are the guy who asks all the right questions and obviously is thinking and paying attention. And your comments always suggest that you're right on top of what I'm trying to say, even when I'm not saying it very clearly. And it is, so many other podcasters are so frustrating to deal with. It's just a great pleasure dealing with you. Okay, I appreciate that. And again, thank you. And folks, I cannot recommend enough, especially if you like economic, but he does so much more than just economics. But again, Steve's blog is great. And of course his books too. I'll link to some of those as well. So the guest has been Steve Landsburg. Thanks, Steve, for your time.
Thank you again, Bob.
Thank you everyone for tuning in. We'll see you next time.
You've just experienced another episode of The Bob Murphy Show, the podcast promoting free markets, free minds, and grateful souls. For more information and to subscribe to this podcast, visit bobmurphyshow.com.